Hello, this is Matthew, and welcome to today's video about the MVSDDT debugger. This is a GUI graphical debugger program we can use from our desktop computer to connect in to an MVS 3.8 instance and do step-by-step debugging of programs that we write in assembly language. This is a hugely invaluable program. Whenever I need to write assembly on the mainframe, I end up using it. It's by Shelby Beach. And the good news is if you're using TK5, or actually even TK4-, everything you need on the server side is already installed and set up in your mainframe. You just need to grab the client for your desktop machine. And later on in this video, I will also show you how to install all of the server-side components in an MVS instance that doesn't have them, such as if you build your own system using Jay Moseley's sysgen instructions, like I usually do for my MVS instances. So first things first, you will need to download the actual program that you can run on your computer. So if you just search for MVSDDT, here it is. It's the first hit on Google here, MVS Dynamic Debug Tool. And it explains a bit about what it does, but essentially you're able to debug both batch jobs and TSO command processors for if you're wanting to debug some programs that you wrote for TSO. And it uses a Java application on the client side to give you the graphical interface to debug your programs. So we don't need screenshots because we're going to actually run it and give it a try. But if you go down to downloading and installing the MVS DDT package, here's the latest release here, DDT 4.0.0. So I'll install that. If we go to the bottom here, you can see who developed it, Shelby Beach. Shelby was also heavily involved with the implementation of the TCP/IP instruction macros and the package in MVS to use the TCP/IP sort of fake instruction that we can add to Hercules. So really prolific contributor to some of the really interesting, more modern things that we're able to do with MVS 3.8, despite the MVS 3.8 operating system predating MVS from ever having any actual TCP/IP support, and certainly predating having a nice graphical debugger tool. So the way this works is that the application running on your computer actually talks to MVS over a simulated CTC, channel-to-channel adapter. And this very program, the MVS DDT, was what inspired me to start working on my, unfortunately, perpetually on the back burner, HTTP API service for MVS 3.8. Taking advantage of the fact that these CTC devices were in fact supported originally in MVS 3.8, and Hercules supports emulating them. So even without the new kind of not real TCP instruction that newer versions of Hercules have and that has been integrated into MVS 3.8, if you install the software that uses it, this is all using stuff that was originally in MVS 3.8 and works all the way back to the Hercules 3.x line of emulators, because it doesn't depend on any of those new sort of artificial instructions. So it's a really cool approach to doing things, kind of combining the best of what we can do within MVS with all the capabilities that we have from a GUI Java application that we can run on our machine. So that's downloaded. I'll close the web browser here. And if I just start up a terminal, you can see what I got in the download is I got my install zip. So I'll unzip install zip. That gives me an install.jar file. This is a executable Java archive. So if you have Java installed, you just run it by saying java-jar and give it that file name, install.jar. And this launches a little installer that will unpack the stuff where you tell it to. Personally, I'd rather the materials just be distributed in a form you can just unzip yourself. I don't really like having to run installers on my computer. But I think it's fine. It's not doing anything too bad here. So there's a license agreement. We can accept the terms of that. By default, it will just install it into an MVSDDT directory in your home directory. So that's fine. It doesn't need root privileges. It doesn't need to do anything system-wide. It's just local to your user. And it talks through what you need to do here. And again, importantly, the server side still needs to be installed on your MVS system. It's already installed in TK5, so I'll start by demonstrating it there. The client will give you that client package, and then the server gives you the files that you'll need to install it on MVS. So I'll leave both of those checked. And it'll offer shortcuts in the start menu and on the desktop and stuff. I don't want it to do any of that, so I'm just going to uncheck that. And we're done. Okay, so as it promised, it gave us an MVSDDT directory. You can see here we have a client and a server. So let's just go into the client. And the client, here it is, ddt.jar. So again, this is an executable jar file. So I can say java-jar ddt.jar to run it. Now, unfortunately, on the recent or almost latest version of Java that I've installed on this machine, there appears to be a bug. But the good news is I also have a, let's see, JVM, I think it is. Yeah, so that was with OpenJDK 22. I also have OpenJDK 11, and MVSDDT works fine under this Java 11. So instead of just running java-jar, I'm going to run the path to that specific Java 11-jar ddt.jar. Okay, and we're in business. So when it opens, you just get this DDT command center, and you can see it's not connected and there's no test active. So we just need to make sure under Options, Preferences, that we set the IP address of the Hercules instance that has the emulated channel-to-channel adapter. In this case, I'm running Hercules on this machine, but you're able to run this on one machine and connect to a Hercules that is over on another machine. So 127.0.0.1 will work there. And then you have to give it all the port numbers that are involved. Now, if we look in, I'm going to go over to my terminal here. And in TK5, in the conf directory, TK5 default, here we go. As you can see, TK5 comes already set up with CTC devices for MVSDDT. So they're at device address 610 and 611. We'll need to know that later. So I'm going to write that down here. And then you can see it creates these CTC-T devices. There are two of them. One is for a command channel and one's for a data channel. That's the way that MVSDDT works. And they each have the server-side port and the client-side port, and then what the client is. So by default, and you can see the way that this is set up in the TK5 configuration is that they have default values that can be overridden with these environment variables. But it's defaulting to our local host. So if I were running this on a different machine, I would need to set the remote side IP address. And it's going to run on these ports, 17.610, 18.610, 17.611, and 18.611. So let's go back over and look at what configuration we need here. The command ports on the MVS side and then the DDT side. So it looks like we want the server is going to be the MVS side, and the client is going to be the DDT side. So 17.610 and 18.610. 17.610 and 18.610. And then the next one was 17.611 and 18.611. So hit save there. We don't need to change JCL. This has the ability to start, to submit JCL, basically to start your tests from here, but we'll just submit it using MVS itself, so I won't worry about that for now. And then we need to tell it the service number, the SVC number that the DDT server is installed in under MVS. As you can imagine, to do step-level debugging and access all the memory and registers and everything, it's actually integrated pretty deeply into the system, and it operates through MVS's ability to add extra service calls to the nucleus itself. So by default, it's installed at service 233 in TK5, so that's perfect. We'll just leave that 233. So with that, if you go up to CTC and say connect, there we go, we connected, green light. And you can see now we're waiting for start of test job. So I'm just going to leave that window over here. And let's go back into MVS. We're done with the configuration file. I'll go to my 3270 emulator, and we'll log on as the HERC01 user. Okay. So I have put a program in here in assembly language. This is actually something I just wrote yesterday based on a discussion that came up over on the mainframe enthusiast Discord, where somebody was asking if there's an easy way to pause between job steps in a JCL procedure where you have multiple steps. And in the ZOS world, somebody suggested running a Unix system services task that then just runs the bin sleep command and provide it a number of seconds you want to sleep, which works, but it seems a bit heavyweight to have to use that BPX, whatever the executable is called, to run shell commands under Unix system services. But also that wouldn't work for our MVS 3.8 because, of course, we don't have the whole Unix subsystem under MVS 3.8. So I thought, it'd be convenient to have a little program that you can just run as a job step. I called it sleep. It takes a parameter that is the number of seconds you want to sleep, and it essentially just receives that parameter. It makes sure that the number is 7 digits or less. It makes sure that every character in the parameter is, in fact, a number 0 to 9, so you can't put a word in parameter and expect it to do something. And then it just uses the MVS supervisor service provided by the stimer macro to wait for the number of seconds. It actually takes hundredths of seconds, so we multiply it by 100, that you want it to wait, and then it returns. And there's a couple error conditions where, again, if you don't supply a parameter, if it's too long, if it's non-digits, it'll return in a binned code instead of running through to completion. So, of course, as I was writing this, I don't do mainframe assembly often enough where I'm able to just do this kind of stuff off the top of my head. And, of course, I had some bugs, and I, in fact, used MVSDDT to help track down some of the things that went wrong as I was writing this. So in this state, the program now works, but we'll still be able to demonstrate how we're able to debug it and watch its execution. So when this whole thing's actually just JCL with the assembly source embedded. So this is going to assemble with our assembler F and then compile that, link it, and it will put it in my HERC01 test load lib library there called sleep. So I'm just going to submit this to make sure that we actually have our program. And if we look at the, I forget, under this is under the Wally ISPF and TK5, so it doesn't quite work to directly launch other tasks from review, but that's okay. We can do 3.8 here. Yep. And then if we look at sleep, I just want to confirm, zeros all across the board. So that's installed now. Okay, and then this takes me back to my review task. Perfect. So normally to run this, let's make a new, let's just say run SLP for run sleep. We need to make our job here. So this would be herc01 sleep job. Let's see, class equals A, message class equals, I normally use X. Does X work on TK5? I think H works for held output. Actually, I think they both do. I'm going to stick to using what I always use, which is X. And this is just a simple, we'll just run the program called sleep, and it takes a parameter. We can sleep for 5 seconds. I think we'll need a step lib, which is where this program lives. So that's going to be herc01.loadlib. Is that where I put it? Yeah, I think that's where I put it. And that should be it. Let's go ahead and submit that. Okay. Start a new window here. And if we look at that, oh, no, we failed. What did I do wrong? Sleep steplib dataset not found. Oh, because it's herc01 test.loadlib, I believe. Let's clean these up. Yeah, I think it's test. There we go. Okay, when we get the underline here in review revEdit, that means that we are in fact referring to a real data set that's there. So submit that. And okay, it's running. It's going to take 5 seconds to run because we told it 5 seconds, and now it's done. So let's just review that. Yep. So that ran, and you can see it took from 307 and 23 seconds to 307, 28 seconds. So sure enough, this program that sleeps for the 5 seconds that we asked it to sleeps for 5 seconds. So nothing new there. That's just you watching me write some boring JCL. What we want to do is run it, but debug it. So I think I actually probably shouldn't have deleted my job output from assembling it because we will want to reference the assembly listing. So let's just rerun that. Okay, and you'll see why we want the listing because that's really how we're going to understand what our program is doing. But if I go over to the DDT command center and I go DDT manual, it has comprehensive documentation, nicely organized here so you can jump to the sections. And this is where it goes over what we talked about of the CTC definition, which is already built into the TK5 configuration for you, and how you set up those ports and the IP address. It talks about if you're running it on a different system, and even over a WAN, as long as you have these ports, whatever ports you configure mapped through your firewall, DDT can be running anywhere in the world and your mainframe can be anywhere else in the world. But the important thing here is how to initiate a DDT test. And one of these, yep, here we go. So you can automatically modify the JCL. Like I said, it's able to sort of submit jobs for you, but I usually just run it myself. Here we go. Yeah. So this is essentially what we're doing, right? We have our exec line, we have our step lib, and then you have whatever else your program needs. In the case of the sleep program, it doesn't need anything. So instead of running your program, you run MVSDDT, and then you give it a parameter list. The first parameter is the program you want to run. And then the second parameter is what you would have provided as the parameter to your program. And you, again, need the step lib, and you tell it what units the CTC devices are on. So the command and the data units. So I'm going to bring this, actually, can I move this over to this window? I'm not going to maximize that. Let's see if we can get this kind of side by side here for reference. So if I go back to my JCL that runs my sleep program, instead of calling sleep with that parameter, let's comment that line out. We're going to run program MVSDDT, and then its parameter is going to be my original program. And then I will give it, there's little quotation marks in the example here, so I'll use them. I'm not sure if they're necessary when there's only one value here, but it won't make a difference to what sleep receives. So I'll pass it that 5 parameter for what the original parameter was. So MVSDDT will essentially launch this program and then pass it whatever parameters you have here. Then we also need to give it the pound DDT CMD DD line. That's going to be unit equals 610 and pound DDT data at unit 611. Okay, I think that's all I need from the manual. So I'm going to close the manual. I'm actually going to bring the command center over here. Now, when I submit this job, there we go. So MVSDDT on the server launched my sleep program and is communicating with this DDT command center over the channel-to-channel adapters that Hercules is emulating. And Hercules provides IP, TCP/IP socket connectivity to act as the other end of the channel-to-channel adapter. So this Java program is talking to Hercules over IP, and then Hercules is translating with its little protocol of how it implements the channel-to-channel adapters. It's translating that to what would look like a channel-to-channel adapter within MVS itself. So already we can see that we know we're running the sleep module, and we're in the sleep csect within it. And you can see here the address, 0A5230. This is the virtual address space that this module was loaded in. And it popped up a disassembly of that csect. And you can see that we have all of the registers. So register 0 through register 15, we can see the full 32-bit value in hex in each of the registers. We're able to start the program. We're able to step each instruction at a time. And particularly cool, if you go up to testing, we can make watch lists. So if I do new watch list window, I'm able to set up variables or locations in memory that I want to keep an eye on. And we can also do a new storage window. This lets us look at arbitrary ranges of addresses in our program's virtual address space in a memory window. So we'll look at all of this in a minute. What I want to do is bring up my, let's go to 3.8 here and bring up the listing of when we compiled this or assembled this. So let's look at that. Okay, here we go. So the assembler gives us the listing as it assembles our program. And you can see that for every one of our assembler instructions here, we see what gets assembled over on the left. So the opcode is going to be at the beginning. ST is opcode 50. It takes a register. 13 is register D. So if you're familiar with all of the instruction formats, you can sort of figure out how everything's being assembled. But it also gives us the address over here on the left-hand side. Now remember, programs on MVS are relocatable. So where your program gets placed in the processes or the address space's virtual memory is up to the operating system when it runs it. So we know that this instruction, this load address instruction, is going to be at address A, so 10 bytes into our program, relative to wherever it gets loaded in memory. And that's why we have this using syntax in assembly programs. And when you generate instructions, all of the storage addresses are relative to a base register that'll show up in each of the instructions. So this isn't a assembly programming tutorial, but just sort of pointing this out, that one of the problems we need to solve, in fact, if I go down and look at my variables that I might want to monitor in that watch list, right? So I have sort of storage set aside for the packed representation of the parameter, and that's a double word. So that's 8 bytes in memory. I have the interval, which is a full word, 4 bytes in memory. That's going to be the binary representation of the number of seconds that we want to sleep. So these are in memory at address F8 relative to the beginning of my program here, and at hex 100 relative to the beginning of my program here. So if I go over to DDT, to our CSEC that's running here, and if I make a new watch list window, and in my watch list, I'm going to right click and say new watch item. And I want to see in memory what gets put in this packed variable. So I'm going to say packed. It doesn't have to be the same name, but it makes sense to me that I call it what I called it in my program. And the address here for packed is F8. So I can just put F8 there. And then qualifier is how I say what this F8 is relative to. Now, as we can see, MVSDDT knows where this CSEC was loaded in memory. So I put in sleep.sleep, which is the sleep CSEC in my sleep load module. And that will automatically find address F8 relative to wherever this module is loaded in memory. And this is a double word, so that's 8 bytes long. And then it will actually decode some different types of data. I can just look at the raw hex value in memory. I can say it's character data, in which case it'll print out the EBCDIC string, packed decimal, zoned decimal, unsigned binary, signed binary. So the binaries will show me the number instead of the raw hex. It'll show me the number in decimal. And then packed decimal and zoned decimal will also show me the actual decoded number for these two different storage formats. Now, this is going to be a packed decimal value in memory, so I'm going to pick packed decimal, and instead of seeing the raw hex, I'm going to see the actual, if it's 32, I'll see 32. Okay, so I'm going to do the same thing for interval. Interval is at address 100 relative to sleep.sleep. It is a full word, so that's 4 bytes long. And that is an unsigned binary value. That's how I want to treat it. So that's how it's going to decode it and display it. So I can put my little watch window off to the side here. Getting back to our main program here, if I go back to the beginning, here we go. So the disassembly should look relatively familiar. It should look like what your listing looks like here. But obviously the advantage of having the listing available is that you can actually follow along with the original program's source code, any comments, and you're able to see things like, okay, save. This was a macro instruction, or a macro expansion. So you're not going to see a disassembled entry for save, because you can see here that save doesn't actually produce any assembled output. But save is an OS provided macro that expands into these two instructions, one of which doesn't assemble into anything. This is just getting half-word alignment. But then it runs an STM instruction, which assembles into this 90 opcode and then these parameters. So sure enough, the first instruction over here that we see in the disassembly is the STM, because that is really the first actual assembled output. And just as you scroll through, right, you just see in memory everything that's there. You can see we get to the point here where we stop being able to decode instructions. So this is just data space that is allocated in the assembly stream here. And so that's going to correspond to, here's our branch instruction to register 14. But then you see here's where we have our save area, which is 18 full words, followed by our other variables. So those are just here as data in memory. It's all starting out as 0. And then it was able to disassemble our pack instruction. So I have a little model instruction here that the execute opcode, the EX instruction, is going to run. So that gets assembled into an actual instruction. And you can see here that sure enough, that has been disassembled back into that pack instruction with those parameters. So what I usually do is I'm on a bigger monitor. I have 2 monitors open. And as I step through my program, I just also scroll through my listing here, which maybe you have printed out, maybe you have in Virtual 1403, so you have a nice PDF where you can actually read the full width of the thing. But however you want to do it, you want to keep your listing available, and you want to keep your DDT window here available. And you can step through one instruction at a time. So let's start doing that. So if I click step, it runs the first instruction. It updates the values in memory in the watch window, and it's now paused at the next instruction. Once again, hit step. It executes that one single instruction. It'll highlight any register values that change between the previous instruction and the current instruction. So you can see the value in register 12 changed. And that actually makes sense because that is the BALR instruction is where we told it to basically branch to the current location and put the address in register 12. That's part of the normal flow of how you establish addressability in these assembly programs. And we're going to load an address into register 13 in the next instructions. You can see that changed. And now we're going to load register 1 into register 2. The address that register 1 points to, actually, the value at the address that register 1 points to into register 2. And that's actually where the parameter list lives. So a really cool thing we can do here is if I double click on this register, it treats it as an address and it opens a memory view at that address for a default length of 256 bytes. You could turn that up if you want to see more of what's in memory at this address. But in this case, this is plenty. Because what's really cool here is this now, based on the address that I loaded, is actually the parameter list that was passed into my sleep program. And you can see right here, the first 2 bytes of the parameter list is the length of the parameters. And the length here is 1 byte. And in this case, the 1 byte is the EBCDIC character F5, which is the character for 5. So that exactly corresponds to the fact that I passed in the parameter 5 to my program to sleep for 5 seconds. So that could be helpful to have up and reference as I'm looking at the logic and the address offsets, later in my program to try and figure out what's going on. One thing you'll note here in the watch list window is that my packed decimal value is all red. It'll highlight red if there's an address error, or in this case, a data error. The data currently at this memory location is not a valid packed decimal set of data. All zeros is not a valid packed decimal representation of any number. So it's highlighting for me that something's wrong here, but that's okay because we haven't actually gotten to the point of the program where we put anything at that point in memory. So I'm not worried about that yet. In any case, as you continue stepping through your program, executing instructions, you're able to step through it just one instruction at a time, which is really, really convenient. Now, if you don't want to step through one instruction at a time, right? If your program runs fine up until later in the program and you really just want it to run until you get to the point where you think, I think it's this store call that's causing my append, and I want to see what addresses are in the register when I get here. If you right click on the address here and set a breakpoint, you can see it now highlights in purple. And if I just run the program, it'll run up to that point. So it ran all the instructions up to this point. Now I'm at address 68, and I'm paused at this instruction right before it runs it. Now you can see that at some point along there, we actually read that 5 from the parameter list, and we converted it into a packed decimal representation of the number. So now my packed variable I can see is actually correctly set to +5. So that's good. Now I can step over this instruction that we set a breakpoint at. And in fact, that's the instruction that stored the converted to binary and multiplied by 100 value. So my interval now has 500 milliseconds. And we can see that because this little watch window automatically updated when that value changed as I'm stepping through the program. Now, eventually, this is going to call the service that actually does the sleep. Let's say we want to skip beyond that. We want to skip all the way maybe to the end of our program. So looking through here, I'm not quite sure, let's say, of where my kind of normal quit function is. So this is where I can go back to my listing from when I ran the assembler, and I can see, okay, quit here is at address 9C. So that corresponds to here, 9C, and I can set a breakpoint here. And now if I hit start, the program will run until it gets to this instruction here at address 9C. Now we said sleep for 5 seconds, but because this is running under the debugger and every single instruction is being evaluated, it does slow the program down, understandably. So interestingly, even though we're calling in to a service provided by MVS, that S-timer service, that's getting slowed down as well. So this did take longer than 5 seconds, but it just came back and we're now paused at this instruction. So I'll just go ahead and hit start again to run the rest of the program. And you can see now the program ended. And the last thing you need to do, because in fact, if we look, I'll show you here, the program is still running, even though it ended. And that's because the MVSDDT program, remember, which is what we used to run our program, is still running because we still have this open. The last thing you do is you say testing terminate. And that then ends the job. And we can see here, it's on the output queue. So if we select that, you can actually see that our job log said that DDT server is running unauthorized. So DDT is able to debug authorized programs, but because our sleep program is not authorized, the DDT server runs unauthorized. So that's a normal message. That's not like, something's wrong, DDT server is running unauthorized. And then we got to the point about 15 minutes after we started it that the program under test has ended normally. And then a little bit later, we sent that termination request, and that's what ended the whole process there. So I hope you can imagine how useful this is for debugging your programs that you wrote in assembly language on MVS. Being able to look at any location in memory, being able to see the actual values that are getting into the registers after you execute each instruction. You can make sure that you're doing your math correctly to get the offsets and the addresses that you're expecting. You can trace the program flow through loops, right? You can hit step, step, step and see if it jumps back up to the beginning of the loop, step, 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 see when it eventually leaves the loop. So it's a super, super useful program. And I know there's the test command in TSO that I think is some kind of debugger, but I've never bothered learning how to use it because I suspect it would be relatively painful. Whereas this is just amazing because you can just see everything in a nice graphical user interface here. So this is a really, really handy program to have if you're doing any kind of assembly language programming on MVS. It does have, if I bring up the manual, it has some other features. You can, I think, tell it about some data structures. Again, you can have programs that have multiple modules with multiple sections. Debugging multitasking programs. I haven't even read any of this. It has the ability, we talked about breakpoints. It has some conditional breakpoints, so you only stop if certain conditions are true. It's a really full-featured, capable debugger, right? It's not a full symbolic debugger that already has the symbols of your program loaded, right? Because it's just essentially entirely based on a disassembly of your program, which doesn't have that info. But in terms of what it can do, it's really, really useful. And I think there was one other thing I wanted to look here that I haven't actually tried, but when you install it, it installs one macro into your macro library. And I think you can actually code breakpoints into your source code itself and assemble them into it. So again, if you're interested in that kind of stuff, definitely read through the manual here, because this tool has some tricks up its sleeve that go beyond what I just showed in that simple example there. And like I said, if you're running TK5 or TK4-, it's all pre-installed. So as you saw, all I needed to do was just install this client program and then configure the address and the ports to match what already came configured in TK5. So when I'm all done here, I can just disconnect. So this now disconnected the connection between this little Java program and Hercules. And you're ready to close that and go about your day. Now, I don't usually use TK5. I usually use my MVS system that's built using Jay Moseley's instructions. So for that, we need to install the server-side components, the mainframe-side components of the MVSDDT. So I'm going to shut down my TK5 mainframe here. And I'm going to be really bad, and I'm just going to kind of hard crash it there because I don't want to make you all wait for it. Okay, so I'm done with TK5. Let's close all of those windows out. And I'm going to start my Moseley sysgen here. So let's get a couple C3270 windows open, and we'll IPL 150. And we will just start up our system as normal. Okay, we are up and running. Note that this starts up in a grand total of approximately 2 seconds. I'm not quite sure what all the TK systems are starting that makes it take a while, but I've never really noticed anything that I feel like I don't have in the Moseley sysgen once I install some various other programs and everything, but none of them really need to take any time at startup. But that is neither here nor there. Let's look at what I have here. So same deal. I have my sleep program. This time, instead of installing it in my user area, I'm actually installing it system-wide in sys2 linklib sleep. So let's submit that just to make sure that's installed, and also to make sure that I have my listing here. That's not my listing. Here are my listing of the sleep program. So again, this will now correspond with the addresses on of this version of the program with the load module that just got assembled and linked. And we should have, let's see, where was I? 3.4. Yep, so let's edit our run sleep job, create that really quickly here so that we can run it when we're ready. And this is just going to be the same thing. So sleep exec program equals sleep parm equals, we'll just say 1 second. And in this case, because I installed it in my sys2.linklib we don't actually need a step lib yet. So if I run that, here we go. Yep. So it took 1.01 seconds to run. So that corresponds with the 1 second sleep. Okay. So our program works. That's all there. What we want to do is install the server components. So let me switch to another desktop here, and let's go back out and look at what we got in that MVSDDT directory. We got the server directory. So this has some JCL and a tape image. So this JCL is going to install the material from the tape. So let's look at the JCL. Okay, DDT serve, message class X, that's fine. Now, the way this JCL is set up by default is it's actually going to install everything under a new high-level qualifier DDT. So it's creating an alias. In this case, we would need to change the alias name for the Moseley sysgen. It's going to create a DDT.load library here, and it's going to create a DDT.maclib library here on the Pebo2 volume. Once you do that, you would then need to move the relevant pieces from those libraries into your system-wide libraries if you want it generally available. So what I'm going to do is change this job to not install those into private libraries, but to install them system-wide to begin with. So we don't need a new alias for a new high-level qualifier because we're not going to create any new data sets there. And we'll still read it from tape. That's good. But instead of creating a new load library, we are simply going to put it in the existing sys2.linklib, which already exists. So sys2.linklib, disposition shared, perfect. And then same thing down here. Instead of installing into ddt.maclib, we're going to install into sys2.maclib, which I believe already exists. Let's double check that. Sys2. No, there is no sys2.maclib. Okay, so we're going to do something that you shouldn't do, which is we're going to install its macro into sys1.maclib. But yeah, typically if you're going to be adding your own assembler macros that you want to be available kind of generally for your user, you'd set up a sys2.maclib, and that's where you'd put your user generated stuff. But for the sake of expediency, just to demonstrate this process, we will install them in sys1.maclib. And again, this macro it installs is this DDT break macro, which allows you to embed hard-coded breakpoints right in your code. So with luck, I can use the submit script to submit batch jobs to the Moseley sysgen. We'll run that. Now, if I look back at my MVS console, right over here, it should be asking for that tape. So it's asking me to mount the tape DDT server on device 100. So I'll go to my Hercules console. We'll say devinit 100. And relative to the directory I was in when I started Hercules, I think that's going to be, yep, MVSDDT server. What's the tape called? MVSDDT.het. Okay, so it's as simple as that. We just ran the job. We're giving it the tape it asked for on the device it asked for. If we hit enter there, I'm going to go back to the console. And sure enough, you can see both of those IAB copy jobs ran successfully with a result code of 000. So if I go back into my TSO session, if I look at sys2 now, sys2.linklib, which is where we told that job to restore those items from tape to, sure enough, we have MVSDDT here. We have DDT, DDT sim, and then we have this funny IGC0023C. So we're going to need to talk about that in a minute. And presumably my sys1.maclib now has that that break macro, but I've actually never tried using it, so I don't have anything to show for that right now. Okay. Let's start the client again so that we can bring up the help. So again, that's going to be, in my case, I need to use that Java 11 runtime, which I believe was, yep, Java 11 bin java -jar ddt.jar. So if you open up the manual, I'll maximize this. Sorry, I don't think I can make these fonts bigger right here. If you look down at the bottom in the appendix, server installation, this walks you through everything you need to know about how to install this and run this on your server. And the important thing here to know is that the MVSDDT program should be in an authorized library. In this case, our sys2.linklib is authorized, so that's good. And then the service routine, which was that IGC0023C file, must be installed in sys1.lpa-lib. So this is how you install additional services into MVS. Basically additional syscalls, I think, is maybe the best way to describe them. Now, the way the number gets assigned is kind of funny. This 23C corresponds with service 233. But you can't just pick any number you want. Your sysgen, or at least your last IO gen, has to have allocated these SVC numbers with certain parameters. So DDT is telling us that it needs to be a type 3 service that holds no locks, is preemptible, and does not require APF authorization. Now, in the TK4- and the TK5 system, that default service number of 233 met those requirements, and it was a service number that was available to be allocated. If we go back and we look at the JCL that performs the sysgen on Moseley's system, which is in the JCL directory, and it's going to be the sysgen 01, not 02, the sysgen 01 step. So this is where all of the devices are defined, all sorts of the stuff that goes into the MVS sysgen. If I go all the way to the bottom, I think the service definitions are, yeah, here they are. So here's a nice little ASCII art chart that shows what these different service parameters are in the service table macro. So this is where we see like service type 3. Well, that sounds familiar because we needed a preemptible type 3 service. So non-preemptible is optional. So preemptible then would be the default. Here's the authorization. Here's any locks it holds. And here's the type of service it is. So if we look at the ones that were in the system I generated, we can see that we have these 240 through 255 services. So, okay, 240. Well, no, 240 is a type 4 service. We need a type 3 service. Okay, the next one up. Aha, service 241 is a type 3 service. And this FC00 thing essentially means that it is not APF authorized. So that's good. That's what we want. So FC00 is good. And there are no locks because there's no -L anything parameter. And this is just an open service for us to use. Okay, so we will use service 241 for the MVS DDT service. Now, while we're here, let's also look for where any CTC devices were generated. So I just searched for the word CTC, and sure enough, we have 4 CTC devices at addresses 500, 501, 502, 503. So when we add the CTC device to our Hercules configuration, remember it was at address 610 and 611 on the TK5 system. We're going to use addresses 500 and 501 because those are already generated into our system because I just used basically the default sysgen macros here, device definition macros that are used in the Jay Moseley system. Okay, so we got our service 241 and we have our CTC devices. Actually, we have quite a few CTC devices generated, but we'll just use the first one here at 500. So back to the instructions. So remember, we need the service handler to go into LPA lib, but instead of it being named IGC0023C, if we want it to be the handler for service 241, it needs to be named IGC0024A. I guess just the weird naming convention in MVS. There's some MVS manual that tells you exactly how to calculate those names, but essentially they start like again, right? C is for 233, so A would be 231, B would be 232, and then C is 233. So similarly for 241, we want 24A. So let's go back into TSO here, and again, if I look in sys2.linklib where we restored all that stuff, you can see the current item is there and it's named that default for service 233. So let's use the utilities. There's a move copy utility. So I'm going to move a data set. So I put M up there for command, and then I'm going to copy or move it from sys2.linklib, and it was IGC0023C was that default name. Now there's already going to be an empty service handler for that 241 in the sys1.lpa lib. So we're going to need to replace the dummy stub handler with what's going to be our new real handler. So I'll hit enter there, and it's asking me, where do I want to send this thing? Okay, so that's going to be sys1.lpa lib. And remember, we need to change the name to 24A. And I'll just hit enter there. And up top here, you can see member IGC0023C moved. Perfect. And our history here confirms, okay, yeah, we renamed it from 23C to 24A. Now we need to do a CLPA, basically clean and rebuild the link pack area for that to take effect and for that service to become available. So we need to shut down our MVS system. So I'm going to log off of TSO. I'm going to go back to my MVS console. We're going to stop TSO. We're going to shut down VTAM. I'm going to stop all of JES2's initiators. And I'm going to stop JES2. And as soon as it says that JES2 termination complete, I'm going to say Z end of day and then quiesce. Okay, so the system shut down. I'll go to the Hercules console. Now, you might think, oh, I'll just re-IPL here and then do my CLPA, but we actually want to add that CTC device to Hercules, which of course you can do manually by typing it all here and attach the, the 500 command. But I want it to be persistent, every time I start Hercules. So I'm actually just going to quit Hercules and edit my Hercules configuration file. And then down at the bottom, I'll add that 500 and 501 device. Now, if you look back in the manual, if you go up to single system connections, Here we go. So these are the lines you want to add to your Hercules configuration file. So the device number, remember, we're going to use 500 and 501 instead of 610 and 611. But I'll leave all the ports just the same number as the example because those will match the port numbers we already configured in the client from the TK5 example. So let's see if that copy paste actually works. It does. Perfect. And then 501, we will use these port numbers. Okay, that's it. So we're getting 3088 channel-to-channel adapters. Again, if you're using the DDT client on a computer that isn't the same computer as you're running Hercules on, change the remote side IP address. And then again, just make sure that the ports are allowed through any firewalls or anything if you're on different networks. This 1024 on the end here is a buffer size, so just leave that as it is. But that should do the trick. I'm going to save that. We'll start Hercules again. And you'll actually see it tries to connect to a remote Hercules instance or whatever else is running CTC as well, right on startup using the remote side port. But failing that, it now just starts a server in Hercules to listen on its local side port, the 17610 and 17611, waiting for connections from that DDT client. So that's good. Let me start up my console and just an extra 3270 for TSO, and we'll go ahead and IPL our system. Remember, we need to do a basically a cold start, a CLPA, so that it picks up that new service we installed in sys1.lpa-lib. There we go. And then Jes2 can just be a regular Jes2 warm start. Okay, I'll start up VTAM. And we should be good to go. So same deal. Let's, we can close the help again. Now remember, we changed the service number. So preferences, and our ports are the same. I think 17 and 18610, is that what we actually said? I already forgot. Yeah, 17 and 18, okay. But if you go to server, we need to change our service number from 233 to 241. Okay, save that. And now I can connect. Very good. Okay, so the network connectivity is working. I'll pull this over here so we can see it. From here. Okay, perfect. So back in TSO, let me go to my JCL. And once again, instead of running sleep, we're going to run the program MVSDDT, and then its parameter is going to be sleep. And then just for fun, I'm going to say 15. So there's 2 digits instead of 1. Okay, now, even though sleep is in my sys2.linklib, which should be in the default search order for programs, when I'm running it through MVSDDT, I found I still need an explicit step lib, sys2.linklib, so that MVSDDT is able to find where it should launch that from. I suspect MVSDDT doesn't inherit the overall system library search path. It may be searching just sys1.linklib by default. I'm not sure. But if you add a step lib here, that'll solve the problem. If you get an error from MVS saying it's unable to find the symbol sleep, just give it a step lib and then it'll be able to find where you have your program installed. So as we know, when I submit that, it should pop up, but it didn't. What went wrong? Do we have a job log here? Oh, of course, I forgot to tell it the CTC devices. Okay, well, so that's good to know. It gives you a nice message here that tells you exactly what you forgot. The DDT data and DDT command DD statements are missing. So let's fix that. I need to give it, it was DDT CMD unit equals, and again, the new one on this system is 500. And then DDT data unit is 501. Okay, let's try that again. Perfect. We are up and running. So again, this is where I would normally make sure that I have my listing of when I built that sleep program available. Because without that, it will be hard to follow along in your step level debugging and, you know, what variables or what memory addresses. But you've already seen how DDT works. So I don't need to show you too much about that again. The one thing I will show you, I mentioned the watch list window, and, you know, it took a minute to set all of that up. One thing you can do, new watch list window. So if I set up those watches again, I'll just do this quickly because you've seen it before. We had our packed at address F8 relative to sleep.sleep, 8 bytes long, and it is a packed decimal. And I'll add this other one, interval at 100, which is unsigned binary. So once you set up your watch list window here. Oh, did I mess that up? Oh, I put an extra period on the end. There we go. So the watch list updates when you do a step. Okay, there we go. That's what we expected to see. You can go to the watch list menu here and save. And I can save my sleep variables. So now as I run through the program, there we go. You can see the parameter came in as a length 2 with the digits 1, 5. So I don't actually want to wait 15 seconds. So actually, let me just get to the point where we get some good data here. There we go. So we got our 15 in there, and we got our 1500 milliseconds. Perfect. So I'm just going to terminate the program early. And since it didn't naturally reach its end, it's just prompting for confirmation, so I'll terminate that. Next time I run the program, so let's go back here and just submit my job to run the program again. When I open that watch list window, I'm able to restore those variables. And if we look at them, you can see that sure enough, the address is correct, the data type is correct. So of course, if I made some changes to the program itself and reassembled it, the offsets for some of your variables might change if you removed a line or added a line that generated more instructions. But if you're running the same test multiple times, you're just maybe trying some different variable values, or even if you did make some changes that change the offsets, this can still be quicker to just update the offsets than to recreate all of your watches, especially if you're watching a lot of memory locations, a lot of variables in a more complex program, especially if you're going between multiple CSECs and you're calling other libraries. Having all of those set up can be nice. And you probably notice here you can actually change the title of this window. So I can say sleep vars, and you can have multiple watch list windows. From this one, testing new watch list window. So if it's a big enough program, right, you may even have separate sets of watch variables, and then you can find them easily in your window manager because you're able to title those windows. So this is a really, really cool program. It saves my life writing assembly programs on MVS because, right, I'll notice all of a sudden it's like, oh, okay, yeah, I see. The address in that register isn't the address that I thought it was. Or I can take an address in a register and look at, if I'm then doing an instruction that is, an index offset of 5, what is actually, 1, 2, 3, 4, 5. Okay. Hex value 41 is what's at index 5 offset from that address. I thought it was 42. I must be forgetting to add in 1 somewhere. I haven't incremented my loop variable correctly. All those kinds of little things that are just the mistakes you make as you're typing in programs and coming up with this stuff. I don't know how I would successfully write assembly programs without this tool. It's really, really valuable. It's really convenient. It's all built into MVS, the TK4- and TK5 distributions. But as you saw, it's also really easy to add. You just restore those items from the tape and put them in the right spot to get it up and running on any MVS system that doesn't already have it installed. So to Shelby Beach, who created this amazing tool, thank you very much. And to the rest of you, thank you for watching. Hopefully, if you've never seen this tool before, hopefully your eyes have been opened to a whole new world of making assembly programming on MVS 3.8 much, much more possible and sort of easier to track down those bugs. Let me know if you have any questions or your thoughts on this tool in the comments. Otherwise, I'm on a couple of the mainframe discords. If you don't know where those are yet, I think there's links in various videos and all of Moshix's videos. So feel free to say hi in there. Otherwise, until next time, enjoy debugging.